actually. So we had talked about homolytic fission, heterolytic fission, and we had talked about the physical properties of alkanes, that they had melting and boiling points which were low. They had weak van der Waals forces, not soluble because they don't form hydrogen bonds. They're not polar neutral molecules. And the reactions of alkanes, pretty much they only had one reaction, which was free radical substitution. You need to know the mechanism. Cl2 and Br2, they react. Cl2 or Br2. They react in the presence of UV light. That's very important. And substitution happens. One of the H atom or all of them or any one of the H atoms in the carbon chain is going to get substituted by Cl or Br. And we talked about the mechanism for that reaction. We talked about free radical substitution, which was that the first step was initiation. And I told you that the UV light breaks the Cl bond homolytically, which basically means that one electron goes back to one of the Cl atom and the other electron goes back to the other Cl atom, and it turns into a free radical. And then it turned into a free radical, and then you had these propagation steps, which were that the free radical, the chlorine atom, would try to gain electrons, and it would steal one of the hydrogen atoms, any one of them, and it would form HCl. And the carbon would be left with just one electron, and it would become a radical now. And that radical would try to complete its bonds by stealing one of the Cl atoms from a Cl2 molecule, and the bond will get completed. And the whole process would repeat endlessly. Every time another Cl radical would come in, steal one of the H atoms, and another of the H atom will get substituted. So it's two steps. Cl comes along, steals the H, forms HCl, and the radical that's formed takes away one of the Cl atom from a chlorine molecule, and the Cl radical is reformed. And the whole process repeats. You can just repeat it, except for this time, the molecule already has one Cl substituted. So there's going to be another Cl radical that would come in and steal one of the H atoms, that would turn into a radical. That particular carbon atom would turn into a radical. And that radical would then try to steal one of the Cl from the Cl2 molecule and bond with that Cl, and another Cl radical would be produced. And it just continues endlessly every time an H atom gets substituted. And then you had the termination step, which was that during all this process, I mean, the free radicals are substances that are missing one of the bonds. So why don't two free radicals somewhere in between just come together and bond with each other? So that's a termination step, that the free radicals, they get used up. If the reaction, so it's kind of the reaction getting terminated, because I mean, the whole chain reaction was happening because of these free radicals. And as soon as I mean, the radicals sort of, if they meet somewhere in the middle, then they would just join up and they would form a molecule, and that's it, the reaction would stop. So it could be any free radical that was produced in the previous steps. Any of them, they can just get together and they can sort of end the process there and then. Instead of the propagation happening over and over again, the reaction would just stop. So that's free radical substitution. And one thing I told you about free radical substitution is that at no point is the carbon-carbon bond breaking. If you do a free radical substitution of a 2-carbon atom molecule, the products that you're going to get are chlorine substituted molecules, which would either contain 2 carbon atoms or multiples of that, like 4 carbon atoms. 2 ethyl radicals can get together and they can form a 4 carbon atom molecule. So the products are going to be in multiples of that. I mean, you're not going to get a 3 carbon atom molecule. You're going to get a 2 carbon atom molecule, or you're going to get a 4 carbon atom molecule. You're not going to get a 3 carbon atom molecule. So we did the butane free radical substitution, and we did something similar, that the bromine radical would come in, steal one of the H atoms, the carbon would turn into a radical, and so on. The carbon radical would then steal the bromine, and the reaction would continue. So the whole point was that if you're doing free radical substitution and you got all these, you got this molecule over here, this one over here, what's going to happen is that any of the carbon atom could turn into a radical somewhere in the middle, and the chlorines will continuously get substituted. So you can get, this one could turn into a radical, this could turn into a radical, this one could turn into a radical, or this one could turn into a radical. These two are the same, that this one and this one were kind of similar carbon atoms. They were CH3s that were attached to this carbon atom. So whether this one turns into a radical or this one turns into a radical was kind of the same thing. And the point is that you'll get a number of different combinations. And if you get a number of different combinations, and remember, not only this, even this one would have a number of different versions. Like different chlorines will be substituted over here during each propagation step. So even the radicals that are getting formed, they would have a number of different versions of that. TK, is this point clear so far, everyone? Anna, clear? Abdullah, is this clear? Ania, is this clear? So we had stopped at monochloro substitution, which was I was trying to do some example questions, and I said that there's a free radical substitution reaction. I told you there was a question on this, and in that, just one chlorine atom was getting substituted, and they told us in the question that you're going to get these two molecules. So the thing is, they were just asking what is the probability of getting this and what's the probability of getting 2-chloropropane, and what's the probability of getting, so this one is 2-chloropropane, and this one over here is 1-chloropropane. So they were asking for the probability of getting these molecules. Propane, actually. So 1-chloropropane. Chlorine is on the first carbon atom. Now the thing is that the probability is that if Cl gets substituted at any one of the hydrogen atoms, these ones, any one of them, it's going to be called 1-chloropropane. Like the Cl would be either on this carbon atom or it's on this carbon atom. It's still 1-chloropropane. So they were asking for the probability of getting either of the two molecules. So if any of the 6 hydrogens over here that get substituted, any one of them, then it would be 1-chloro. It would lead to 1-chloropropane. And if any one of these hydrogens over here in the middle, they get substituted. So the green ones, these ones, if they get substituted, you get 2-chloropropane. And if the ones on the side, they get substituted, you get 1-chloropropane. So you had to find out the probability of getting which of the substitution products, like 1-chloropropane. So out of the 8 hydrogens, so let's assume that there's an equal probability of substituting any of the 8 hydrogen atoms. For example, if a Cl comes in and substitutes this H atom, or the Cl comes in and substitutes this H atom. So we're assuming that it's an equal probability of getting, they all have equal probability of getting substituted. So the point is that when would you get 1-chloropropane? So out of the 8 hydrogens, 6 of them are going to lead to 1-chloropropane, like these ones. You substitute any of these hydrogen atoms, or you substitute any of these hydrogen atoms. Okay, just one monochloro substitution, just one chlorine atom substituted anywhere on any of these hydrogen atoms. If they get red and you put a Cl in its place, it's going to form 1-chloropropane. So the probability is that out of the 8 hydrogens, 6 of them If they get substituted, that would lead to 1 chloropropane. And 2 chloropropane would be formed if out of the 8 hydrogens, the middle 2, if any of the H on the middle carbon atom, they get substituted by Cl, that leads to 2 chloropropane. So out of the 8 hydrogens, only 2 of them would form 2 chloropropane. So the probability is this would be what? 3/4, which is 75%. And this would be 1/4, which is 25%. So 2 chloropropane would be, the probability of getting 2 chloropropane would be 25%, and the probability of getting 1 chloropropane would be 75%. Okay, is this clear? Zari, is this clear, Zahib? And now, Anya, do you get this?
Yes, sir.
Okay, so that's just one type of question. Then there was another type of question, which is that they might ask you about the possible products you might get during a substitution reaction. So let's say they're saying that propane undergoes free radical substitution. And there might be, anyway, so there might be a number of, so there would be a number of different molecules that are possible. So propane is this thing. Okay, so propane is this thing, and they're asking what are the possible products of free radical substitution. I mean the end product, like that after the termination step. So one of them they gave us was this one, that it had a Cl. It had a Cl over here, and it had H atoms. So that is clearly possible. I mean, that is what you're going to get if you do a substitution reaction with chlorine. So that is fine. There's nothing wrong with that. This one is definitely possible. Then they gave us this one, and they said that this is a possible product.
So do we have to remember the ones that they might give us?
You don't have to, like, I just told you that when free radical substitution is happening, I mean, just need to know what the idea is, that any of the H atoms can get, like this H atom over here, it might get substituted, right? So you could get a Cl in its place. Do you get the point?
Yes, sir.
Or any of the H atoms. So it's quite possible that the H atom over here got substituted and the H atom over here also got substituted. Is that clear, the first one?
Yeah.
Now, the next one is this molecule. And the question states, is that a possible substitution product when you try to do free radical substitution for this molecule over here? So is that a possible product of free radical? I mean, is that a possible free radical substitution product? Now, if you look at this molecule, I told you that during the propagation step or during free radical substitution, when the Cl radical comes along, any of the H atoms could get knocked out and a free radical would be formed. Any of the carbon atoms, they could turn into a free radical. Like even if we go back further, a bromine came along, it could steal any of the H atoms, and the carbon could turn into a free radical. Any of the carbon atoms could turn into into a free radical. So the idea is that as free radical substitution is happening, it's going on. So this might happen that you have it's a 3 carbon atom molecule. A Cl radical might come over here and would try to steal this H atom, right? And join with it. It would eventually form HCl. So what would be left? What's going to be left is that the middle carbon atom would turn into a free radical because it's going to be short of one bond. Okay, so the middle carbon atom could turn into a free radical. Is this point clear? This one? Yes or no? Is this clear? Abdullah, is this clear? Hania? Anna?
Yes, sir.
Okay.
Yes, sir.
And it's also equally possible that the Cl radical comes along and it steals some other hydrogen atom, like the one over here. So the Cl radical comes in, it wants electrons, it takes the H atom and its electrons and bonds with it. So what you could also get is, I'll just copy paste this molecule. So what you'll also get is this molecule, which I'm going to draw over here. And the H atom over here is now missing. So it has turned into a radical, right? So a number of different radicals are possible. So I'm just looking, can I get this molecule or not? So if you look carefully, then two of the radicals can sort of, if I try to rotate this, then you'll notice that, the radicals over here, if I just shrink it a little bit. So what you'll see is that the first carbon atom is a radical. It's a radical at the middle carbon atom, and this carbon atom is a radical, and it's forming a free radical on the carbon at the end. They both need one electron each, so they might start forming a covalent bond with each other, and they would link up. So they might link up in the middle over here, which is going to give you a molecule that would look exactly like this. Except that during the process, the Cls are constantly getting substituted. So the Cls could randomly get substituted at any of the hydrogen atoms, but you can get this molecule. Is this point clear? Is this clear? Yes.
Sir.
So could you explain that again, please?
Okay, I was just saying that, remember you had propane, right? So I'm just going to take this off. So you had propane. I told you that in the first step of free radical substitution, what happens? Like if you go back, not the first step is, the first step is initiation. That's where the radicals are formed. The Cl radicals are formed. And then those Cl radicals, they start attacking the hydrocarbon molecule and they start stealing hydrogen atoms from the carbon atoms, right? And the carbon atoms, they turn into radicals. Hani, is that point clear?
Yes, sir.
So now the thing over here, what's going on here is that, where's the molecule? So I told you, I started off with propane, right? So the Cl radicals, like we're doing free radical substitution. So the Cl radicals would come in and they would steal any of the hydrogen atoms. So they could steal a hydrogen atom from the middle carbon atom. If they do that, let me just correct this. So if they steal, then this carbon atom would turn into a radical, right? What a radical means is that it's short of one bond. It's supposed to make 4 bonds, but right now it's making 3 bonds. It's got an electron, but it's not paired. Or you could have a radical at the end of the carbon chain, like a 3 carbon atom chain, and the last one is a free radical, right? Anya, is this point clear?
Yes, sir.
So the point is, in the termination step, what happens? Like this carbon wants to make a bond. This carbon also wants, the one over here also wants to make a bond now. So in the termination, the last step, any 2 random radicals that were produced during the reaction, they might just get together to complete their bonds. So these two would can get together and they could form a bond over here, right? And you will get a molecule which would look something like this. So the basic thing I was explaining was that if you start off with a 3-carbon atom molecule, you'll get 3-carbon atom chlorine substituted compounds. But you might also get 6-carbon atom chlorine substituted compounds as well, because the carbon radicals might join up and you'll get a much bigger molecule. Hani, is this point clear?
Yes, sir. Do you know when you're bonding the things, it doesn't only need to be chlorine, does it? Chlorine and bromine.
When they can bond, like in the termination step, they can bond with, any of the radicals that are formed. Like, where's the termination step? Just a second. For example, this one. For this one, we just did initiation, propagation, right? So the thing is, the main thing is that the carbon atoms, the carbon radicals, the reason we reacted it with bromine was we wanted it to, if one of the bromine steals one of the hydrogen atoms, turns it into HBr, which is over here, right? So the reason we added bromine molecules was that we wanted the carbon that became a radical to bond with a bromine so that you get bromine substituted compounds. That was our aim for this reaction. Hani, is that point clear?
Yes, sir.
But the thing is, maybe this carbon, like if I draw it over here, somewhere on the side. So the thing is that maybe this carbon radical, maybe it's not going to bond, like in the termination step, it might not bond with the bromine. It might bond with a molecule that would kind of, let's say there are 2 molecules exactly the same, right? So it might bond with a molecule that looks, let me just straighten this up. So it might bond with a molecule that looks exactly the same. So because they both are looking for bonds, right? So they might join up. Now, for them to join up, I would have to without redrawing the whole structure, the 2 carbon atoms are trying to link up. So let's just link them up. These 2 carbon atoms might bond with each other. Is that point clear?
Yes, sir.
Okay, so that's the point I'm trying to make, is that it's not always that free radicals, they join with bromine molecules, they can also join with each other. So the termination step is very random. Is the termination step in the previous case as well? In the termination step, it might join with a Cl radical, or it might join with a molecule, kind of a similar molecule, and the 2 carbon atoms might join up to form a much bigger molecule. So you're going to get this. So the point is, so is this clear to everyone, this last molecule that we drew? Is this clear? Alicia, is this clear? Rubab?
Yes.
Okay. So just remember, watch out for this, okay? So I'm going to do, tell me if this is possible. Let's do another one. If this molecule is possible for propane, remember we're still talking about propane. So I've got this molecule, and I've got, so we are talking about propane, so this one. And the rest is all hydrogens and Cls. Okay, so so remember, focus on propane. Can this molecule be produced during free radical substitution of propane, this one? Is that a possibility? Anyone? Is this molecule possible? Like over here, remember, you have to think of it this way, that 2 propane radicals, they join up to form this. So can 2 propane radicals, the radical could be on this carbon atom or this carbon atom or this carbon atom over here. So can 2 propane radicals join up to form this molecule over here? Is that possible? Yes or no?
Yes.
I think so. Yeah.
Okay, it is possible. Why? Because remember I told you that. So I'm going to draw the carbon atoms only. I'm just for clarity. I'm not going to draw the hydrogens around it. So maybe the middle carbon atom turns into a radical, right? So out of the 3 carbon atoms, maybe the middle carbon atom turns into a radical. And there's another molecule. And in that case, also the middle carbon atom turns into a radical. So if the 2 carbon atoms, they connect in the middle, the molecule would kind of look like this. It's going to look like this, that it's 2 propanes. Okay, this is a bent version of one propane. This is also a bent version of the other propane. So it's 3 carbon atoms, and the 2 carbon atoms in the middle are kind of connecting to each other to form this molecule. So they're going to what I can do is I can sort of bend this carbon to the top, and I can sort of bend this carbon slightly to the bottom, and the 2 carbon atoms can get together, and they can connect in the middle. So if they do that, and there's going to be a covalent bond that would be formed. So it's going to look exactly like this. It's 3 carbon atoms. You can add in all the hydrogen atoms, but this molecule would be possible. Clear?
So is it would you be allowed to like bend it?
Yeah, I mean, remember one thing about organic chemistry, like look at this molecule. Remember, this is like, if I draw a molecule here, and this is an important question. So if I have this molecule, right? Now the point is that the structural formula doesn't actually tell you the actual shape of the molecule. I mean, you could have drawn it some other way, like the Cl would be pointing this way. I mean, the H would be pointing over here. This H would be pointing over here. And there might be another H over here. Okay, so the point is, these two are exactly the same, like because these are not the actual shapes. When you draw a covalent molecule and you write the structural formula, what you just show is the connections, like who's bonded to which atom. Cl is bonded to carbon atom, Cl is bonded to carbon atom. So it's kind of the same thing. And the carbon atom is bonded to 3 other hydrogen atoms. The carbon atom over here is bonded to 3 other hydrogen atoms as well. Do you get my point?
Yes, sir.
So just remember, the 3-dimensional shape of the molecule is completely different. Like when carbon is forming 4 bonds, it's actually tetrahedral. It looks like this, where one bond is coming towards you. This is the wedge-shaped bond. The dotted one is going behind the board. So the actual shape of the molecule kind of looks like this. So just remember, these versions are not the actual shape. They just show which atoms are connected to which atoms. So you're allowed to draw, you're allowed to bend it. You're not allowed to break the bond. I mean, if this is propane, right? I mean, the way we were drawing propane, if this is propane, then remember, this is not the actual shape of the molecule. Then this is exactly the same molecule. Like if you just bend it, because both of them, they don't actually represent the actual shape of the molecule. They just show which atoms are bonded or connected to which other atoms. So both of them are exactly the same. Carbon atom with 3 H atoms. So this is also carbon atom with 3 H atoms. The middle carbon atom is with 2 H atoms. The middle one is with 2 hydrogen atoms. The end one is with 3 hydrogen atoms. So these two are exactly the same. So just remember, there's no restriction to bending because it isn't even the actual shape of the molecule in the first place. So is that clear?
Yes, sir.
So the point is that during free radical substitution, the molecules can have many different shapes. I said, let's do another one. Let's say I have, let's do another one. Is this possible? And these are all the hydrogens or Cl. Right? The hydrogen atoms are randomly getting substituted, so we don't really care about the hydrogen atoms. So propane, right? Can you even tell me, is this possible? Like two propane radicals, can it form this molecule? I mean, it can form this molecule. We found that out, but can it form this molecule? Is this possible?
I don't think so.
Okay, this is not possible because even though it has 6 carbon atoms, but there's no way like you can try any 3 carbon atom radicals. This molecule will never be formed. Like you can't even split it into 3 and 3, right? I mean, you can't break it into. I mean, the easiest way is, can you break it into 2 pieces of 3 carbon atoms? I mean, the first one, like over here, I can actually do that. I can break the molecule over here, and I'll get a 3 carbon atom chain, and I'll get another 3 carbon atom chain. So that means the 2 carbon atom chains were connected over here. Over here as well, I can break it, split it into 2. I'll have a 3 carbon atom chain, and I'll have a 3 carbon atom chain. That means the 2 carbon atoms were connected in the middle. Over here, I can't just split it into 3 carbon atoms because my original molecule is 3 carbon atoms. So I can't really do that. If I do that over here, I'll get a 2 carbon atom molecule and I'll get a 4 carbon atom molecule. So that's not possible. No matter where I split this thing up, it's not going to result in 2 propanes getting together to form this molecule. So this one is not going to be possible. Okay, is that clear?
Yes, sir.
Okay, everyone else. Anna, is this clear? Mariam, is this clear?
Yes, sir.
Yes.
So that's free radical substitution. You just have to be careful about what different products are possible. I mean, so it's kind of a random reaction where I mean, you'll be asked about the propagation steps, you'll be asked about the termination products, and you'll be asked about the possible termination products, which are possible, which ones are not possible. And remember the conditions of these reactions as well. Now, alkanes, moving on from here, there's another reaction of alkanes, which it's a small reaction. And that is not really of alkanes. It's basically about cracking of long chain hydrocarbons. Okay, so you get most of your hydrocarbons from crude oil. Smaller molecules have certain properties and they're very useful. Smaller molecules are more useful. And there are a number of reasons why smaller molecules are more useful because they've got lesser van der Waals forces. Remember van der Waals forces? So they've got lesser van der Waals forces because van der Waals forces, the intermolecular forces, you've got more electrons, there'll be more dipoles as well. As because they have lesser van der Waals forces, they have low melting and boiling points and they're volatile. And they're going to be volatile liquids or gases. So they're going to be very, very volatile. That's a good thing because like petrol and the gases that are used for domestic heating, they're volatile. They've got low melting and boiling points. The reason being gaseous or being in liquid state is good is because they can flow through pipes. Like your car runs on petrol because petrol it flows like a water, okay? So it can go through pipes, travel around. So that's a good thing. And they're also less viscous as well, which basically means the same thing, that they would flow easily. So that's another good thing about this. And another property is that they're going to be more flammable as well. Now that has to do with them being gaseous. They'll have more surface area because gaseous substances like petrol evaporates very quickly. So it mixes with air very, very well. So they're going to be more flammable. They would be gases mixed with air easily. Like candle wax will not mix with air. Candle wax, something that's solid, it's not going to mix with air. Gases mix with air easily. So they'll be more flammable as well. So these are some of the good properties. So smaller molecules are more useful. Bigger molecules don't have these properties. They're going to be less volatile. Like candle wax doesn't really evaporate, or it just stays as candle wax. Even if you heat it, it doesn't evaporate. It's got high melting. The other ones high. They're going to have high melting and boiling points. They'll be very viscous. Like candle wax doesn't flow. So I mean, if you fill your car tank with candle wax, then your car tank is pretty much, it's going to be useless because it would be very hard to take it out. And they're going to be less flammable as well. They're not going to mix with air. They'll be attracting each other so strongly that they're not going to allow the air molecules to come in between. So they're not going to be very flammable as well. So what cracking does is that useless long chain hydrocarbons useless long chain or less useful long chain hydrocarbons, which you get from crude oil, mostly obtained from crude oil. So crude oil is that thick tar-like substance. These are broken down into smaller, more useful hydrocarbons. So more and for this, you would need a temperature that should be greater than 450 degrees centigrade and a catalyst. And the catalysts that are used are zeolites or pumice. Now these catalysts are kind of a mixture of Al2O3 and SiO2. So you need catalysts for this. And there's thermal cracking as well. There's another type of cracking. So the molecule literally is cracked into smaller pieces. Thermal cracking requires temperature to be greater than 700 degrees centigrade. That does not involve a catalyst. So better to use a catalyst. Yes, Abdullah.
Sir, I have a question. Why is crude oil basically useless long chain hydrocarbon? This is like breaking the chain, right? So
Yeah.
why is it quite useless? Because honestly, crude oil can produce useful fractions such as the use like what we have done in IGCSE. Why is it useless?
I'm saying that crude oil mostly produces, just one second. TK, let me just come up with the image. TK, this is crude oil, right? So the point is, you do get lots of useful things from crude oil, TK. But most of the stuff, most of the tar-like stuff, TK, bitumen, lubricating oils, waxes, you get a lot of this stuff. But how much, I mean, the world doesn't really need lubricating oil that much. Do you get my point? You need fuel for cars, you need fuel for planes, you need fuel for cars, you need fuel for trucks. You don't need lubricating oil, right? So if you're getting grease and waxes, I mean, you need to convert that. You need to break those down into kerosene or petrol or diesel, TK. You need that, and you don't need to make a lot of roads as well. Like you don't need a lot of bitumen as well, right? So those molecules need to be broken down to get more useful stuff. TK, is that clear?
Yeah. Okay. Sure. Thanks.
So we'll just complete this in the next class then. So I mean, you've already done this. This is pretty much O-level stuff. I'll just add this, that smaller, more useful hydrocarbons. What you get over here is you get a mixture of alkanes, smaller ones, and you get alkenes. And it's also, you get a lot of hydrogen gas as well. So these things are obtained when any of the three things, not all of them at the same time, but and it's a random process. Different molecules are going to crack in a different way. So it's not always that you're going to get, like if you have 1,000 molecules, each one of them is going to be cracked in a different way. So every one of them will either produce an alkane or an alkene, or sometimes it will produce an H2. So, but at the end of the day, you're going to get a mixture of smaller alkanes, alkenes, and hydrogen gas. Okay. So, chalo, theek hai, let's continue with this in the next class then. Okay. Okay, everyone.
Allah Hafiz.
Allah.
Take care. Allah Hafiz.